Welcome back to the Deep Dive. Now, if you're a regular listener, you know our usual routine. We take a topic, maybe it's history, maybe a new tech trend, and we sort of poke at it, we turn it over, look at it from all the angles, have some fun.
We're observers.
We're observers. But
Who?
today
Mm.
is completely different.
The vibe in the studio is definitely heavier.
Yeah.
Much more focused.
It is. I want you to imagine we're not in a recording studio. I want you to imagine we're stepping into a boardroom. Top floor, global headquarters. You know, the mahogany table, dim lighting, very high stakes.
Right.
We are putting on our suits, metaphorically speaking, and we're treating this hour as the formal delivery of the Global SDV Technical Strategy Report for 2024-2026.
And we have to. The reason for this shift in tone is just the absolute gravity of this moment for the auto industry. We've spent, the last 5 years talking about the promise of the software-defined vehicle?
Well, yeah,
The buzzwords, the flashy concept cars at CES with the rotating seats and the hologram dashboards. It's all been innovation theater. It's been fun. But looking at this mountain of reports on the desk today, and we have everything. Data from NXP, from Electrobit, Zetascale, Here Technologies, Hariba Mira. It is abundantly clear that the party is over.
The lights are on, the music stopped, and now it's time to clean up the mess.
That's a perfect way to put it.
We are officially entering what we're calling the reality check phase. This is about industrialization. It is no longer about if you can build an SDV. The question now is how you survive the transition without going bankrupt.
Or just drowning in technical debt.
Exactly. So for the next hour, think of me as your lead strategy consultant. I'm here to guide us through the market findings, the strategic imperatives, using a really strict consulting framework.
And I'll be stepping in as your chief technical architect. My job is to be the buzzkill. I'm going to scrutinize the details, look under the hood of these architectures, and explain why some of these strategies will fly and why a lot of them are going to crash and burn.
Because the industry is facing a massive existential crisis right now. We call it the decoupling paradox.
The decoupling paradox. It sounds like a spy novel, but it's the fundamental friction that is defining this entire 2024 to 2026 period.
Break it down for us. What's the friction?
It's a violent clash of timelines. On one hand, you have hardware development cycles, you're bending steel, you're validating silicon reliability. That takes 3, maybe 4 years. You have to lock that down.
Right. It's slow, methodical, rigid. That's the heartbeat of the auto industry.
It has to be. But on the other hand, you have software development cycles that are moving to weeks, sometimes days, even hours. You've got CI/CD pipelines pushing updates constantly.
And you're trying to decouple them, to let the software run fast while the hardware runs slow.
But they have to meet perfectly at the start of production, or SOP. And if they don't,
Disaster.
catastrophe, you get one of two scenarios. Scenario 1. You've got a beautiful piece of hardware, a stunning car that is essentially a brick because the software isn't stable. We've seen major launches delayed by months because of this.
And scenario 2.
Brilliant software innovation that has no hardware capable of running it because you locked the chip spec 3 years ago and you didn't anticipate the compute load you'd need.
It's a nightmare. And the stakes here are they're astronomical. We're looking at market data projecting the SDV market to jump from around, $391 billion in 2024.
To $1.6 trillion by 2030.
1.6 trillion. It's a massive pie. But to get a slice, legacy OEMs are paying off this staggering amount of technical debt. They're trying to refit organizations built for mechanical engineering into agile software houses.
It's like trying to turn an oil tanker into a speedboat.
Well, it's still moving at full speed.
Exactly. It almost defies the laws of organizational physics.
So to navigate this, we are going to use a very strict McKinsey-style MECE framework for this deep dive.
Yeah.
MECE. Mutually exclusive, collectively exhaustive.
We have to. It's the only way to make sense of the chaos.
So we're breaking this report down into 4 distinct technical pillars.
Yeah.
First, the physical reconstruction, the hardware, the shift to zonal architecture.
The bot.
Then the nervous system, that's the middleware, the communication layer, which is a battlefield right now.
On nerves.
Third, the hybrid brain, the operating system strategy.
Living.
And fourth, the software factory, how you actually build and debug all this code, the tool set. And finally, we'll wrap up with a regional analysis to see who's winning this race: China, North America, or Europe.
A full checkup. Body, nerves, brain, and tools.
This is the roadmap for survival. So let's open the file. Section 1.
Let's do it.
Section 1. The physical reconstruction. EE architecture and hardware. The big headline here is really the death of the domain controller. I mean, for a decade, we thought domain architectures were the answer.
Right. You'd have a body controller, a chassis controller, an infotainment controller. It made sense on paper.
But now the industry is hitting a physical wall.
It's a literal physical wall. It all comes down to weight and complexity. In a traditional distributed architecture, you might have 100, maybe 150 electronic control units, ECUs, just scattered all over the car.
And to connect them all, you need wiring harnesses.
The old nervous system. And it's a mess. These harnesses have become so complex that they are now the third heaviest component in the car.
The third heaviest. After what? The chassis and the engine?
Exactly. We are talking about 60 to 100 kilograms of copper. That's like carrying an extra adult passenger who does nothing but hold wires.
From a manufacturing perspective, that just has to be a bottleneck.
It's a complete nightmare. You can't really automate installing them. It takes human hands to thread these massive snake-like cables through the chassis. It's slow, it's expensive, and it's heavy. And in the EV era, weight is the enemy of range.
So the shift we're documenting in this report is the move to zonal architecture.
Which is a profound change in philosophy. It's not just an evolution.
So explain that distinction for us. Function versus location.
Okay, so in the old world functional, if you had a door lock, it was wired to a central body computer, maybe 10 feet away, the window motor right next to it. It also had a separate wire running 10 feet to that same computer.
So you have these massive bundles of wires running the length of the car.
Right. In zonal architecture location, you place a powerful zone controller in the physical corners of the car. Front left, front right, rear right.
Like little local hubs, regional managers.
That's a perfect analogy. Think of them as the hands and feet of the vehicle. That local controller handles everything in its physical zone. It aggregates the I/O from the door locks, the window motors, the ultrasonic sensors, the headlights, all of it.
It digitizes the data right there at the edge.
And sends it over a single high-speed Ethernet link to the sender.
So instead of 50 wires running the length of the car, you've got one Ethernet cable and a power line.
Precisely. You slash that 100 kilograms of wiring, you reduce weight, increase EV range, and you simplify assembly because robots can now install these shorter modular harnesses. But, and there's always a but in engineering.
There always is.
It introduces a nasty new challenge. Thermals and vibration.
Because these zone controllers aren't sitting in a nice air-conditioned dashboard.
No, they're tucked into the wheel well or a corner of the chassis near the brakes. It's hot, it's vibrating, it's dirty.
And yet, we're asking these chips to handle high power distribution, smarty fuses, and real-time control loops.
That's the thing. A zone controller isn't just a dumb switch. In 2026, it's doing the motor control for the window, maybe the local anti-lock braking processing. It's doing heavy math in a sauna.
Which is why the hardware strategy is shifting so aggressively towards these pre-integrated silicon platforms. I mean, the NXP CoreRide report really spelled this out.
Yes, CoreRide is a great example of this. NXP is basically positioning this as a way to stop the bleeding. The report mentions that OEMs are currently wasting about 50% of their R&D budget just on plumbing.
50%. Just on getting the basic drivers and the OS to talk to the chip.
That number, 50%, is the most damning statistic in this whole report. Imagine building a house, but spending half your budget inventing a new kind of PVC pipe before you even lay the foundation. It's insanity.
So NXP's CoreRide strategy is to offer a referral design. They aren't just selling you a chip, they're selling the whole stack.
They've broken it down into a specific 3-tier hardware stack that maps perfectly to the zonal architecture. First, you have the S32N, that's the central compute, the brain.
Okay.
It handles the heavy lifting, the vehicle networking, the central logic. Then you have the S32Z and S32E processors.
Those are the zonal ones.
Yes. The Z and E series are built specifically for safety and real-time control. They're the ones sitting in those hot corners, managing the brake signals where failure just isn't an option.
Yeah, the third tier.
The S32K, those are the edge nodes, the tiny microcontrollers on the sensors themselves.
And the strategic insight here is that by buying the whole platform, where the S32N already talks perfectly to the S32Z, you reclaim that 50% of your budget.
You stop reinventing the wheel, or, the wire. You focus on the application, the stuff the driver actually sees and feels. If you're a consultant, you tell your client, buy the plumbing, build the experience.
But while NXP is solving the plumbing, there's a war brewing at the top of this stack. The compute arms race for that central brain.
Oh, this is the heavyweights. NVIDIA versus Qualcomm. This is the battle for the soul of the premium car.
And it's a battle of philosophies, really.
Completely. On one side, you have NVIDIA with their Thor platform. NVIDIA's pitch is simple. One chip to rule them all. We're talking about massive raw power, 2,000 TOPS.
2,000 trillions of operations per second. That's a data center on wheels. It's ludicrous.
It is. Their strategy is centralization on steroids. Put the cockpit, the infotainment, the ADSC, the parking, put it all on one giant piece of silicon and virtualize everything.
It sounds efficient from an architecture standpoint.
It is, but it's hot. It requires liquid cooling. It's expensive. It draws a lot of power. But for a premium vehicle that wants a living room experience and level 3 or 4 autonomy, it's a compelling option. You have a supercomputer in the dash.
And the counter strategy from Qualcomm.
That's the Flex approach. It's heterogeneous. Instead of one giant hammer, they offer a flexible soaking that balances cost and power. They're very good at running Android for the cockpit side-by-side with QNX for the ADS side.
So it's less brute force and more optimized integration.
Exactly. It scales down better. A mid-range vehicle can afford the Flex approach. They probably can't afford Thor.
And we can't ignore the China factor here. The report mentions that Chinese OEMs like BYD and NIO are just adopting these architectures way faster than anyone else.
So much faster. And this is a key cultural difference. They view the car as a mobile plus car compute fusion. They aren't burdened by these legacy organizations that separate infotainment from driving. To them, it's all just compute.
So while European OEMs are in committee meetings debating safety, Chinese OEMs are already shipping.
They are willing to adopt these massive centralized chips today. It's a different mindset.
Which brings us perfectly to the next layer. You've got this centralized brain, you've got these zonal hands and feet. But how do they talk to each other? Let's move to section 2, the nervous system, middleware and communication.
This is where the battle is the bloodiest right now, the middleware war. The report identifies a data bottleneck as the critical failure point for most OEMs.
It's a classic pipeline problem. We used to run cars on CAN bus and a line bus. Simple, reliable, but painfully slow.
CAN bus is like trying to stream a 4K movie over a 1990s dial-up modem. It's fine for telling a window to roll down, that's just a 0 or a 1, but now we have 8-megapixel cameras, LiDAR sensors dumping gigabytes of data per second.
So the pipe has to get bigger.
Much, much bigger. The first shift is the move to an Ethernet backbone. We're talking 10 gigabit speeds. This brings IT standard networking into the car.
But standard Ethernet has a problem, right? It was designed for the office. If a packet of my email arrives a millisecond late, nobody dies. In a car, if a brake signal arrives a millisecond late.
That's the definition of a bad day. Ethernet is non-deterministic by nature. It's best effort. And in a car, best effort is not good enough. That's why we need TSN, time-sensitive networking.
Okay, I see this acronym everywhere. TSN. Break it down for the non-engineer. How does it fix Ethernet?
Imagine a highway. Standard Ethernet is a highway where anyone can merge anytime. If a massive convoy of Netflix trucks that your infotainment data merges on, traffic jams up. Your little sports car carrying the emergency brake signal gets stuck.
Disaster.
TSN creates a dedicated express lane with a gate. It's called the time-aware shaper. The network knows exactly when that brake signal is coming. It literally closes the gate on the Netflix trucks, holds them back for a few microseconds, and opens the express lane for the brake signal.
So it mathematically guarantees that safety-critical data is never stuck in traffic.
Exactly. It adds determinism. And it also handles synchronization through a standard called IEEC 802.1AS, or GPTP.
Global Precision Time Protocol.
Right. It makes sure every clock in every ECU across the car is synchronized within microseconds, and this is absolutely vital for sensor fusion.
Give me a real-world example of why that matters so much.
Okay, your car is moving at 60 miles per hour. Your camera takes a picture of a pedestrian. Your radar bounces a signal off that same pedestrian, but the camera takes its picture 5 milliseconds after the radar ping.
Which, at 60 miles an hour, is a significant distance.
It is. If the car didn't know the exact time difference between those two events, it might fuse the data incorrectly and think the pedestrian is in a slightly different location than reality. TSN fixes that. It makes sure everyone is looking at the exact same watch.
Okay, so the pipes are bigger and they're smarter, but what language are we speaking through those pipes? The report highlights a major conflict between the old guard, SOME IP, and these new contenders.
This is the middleware battle. For a long time, the industry used SOME IP. It's a service-oriented protocol. It's fine. It's okay. But it really struggles with dynamic discovery.
What's dynamic discovery?
Finding new devices on the network. If I plug in a new trailer or a new sensor, how does the car know it's there? SOME IP is clumsy with this, and it gets heavy when you scale up to massive data loads. It wasn't built for a data-centric world.
So, enter the challengers. First up, DDS.
Data distribution service. This comes from the defense and aerospace world. It powers battleships. It's a publish-subscribe model. I don't care who needs the data, I just publish it. If you need it, you subscribe.
And its power is in QoS, quality of service policies.
Right. You can tell the network, this data is vital, make sure it gets there, even if you have to retry, which is like TCP. Or you can say, this is fast-moving radar data. If you miss a packet, forget it, just send the next one, don't clog the pipe, which is like UDP. It gives the architect really granular control.
But the report spends a lot of time on a disruptor called Zeno. The Zeta Auto source material is very bullish on this. Why is Zeno beating DDS in specific areas?
Zeno is fascinating. It's being called the unifying protocol. The problem with DDS is that it's heavy. It has a lot of wire overhead, all of the metadata, it wraps around every message. The report notes DDS has 50-plus bytes of overhead per message.
50 bytes doesn't sound like much in the age of gigabytes.
It doesn't, until you're sending millions of tiny messages per second. Then it clogs the pipe. But the bigger issue is the memory footprint. DDS requires a fair amount of RAM to run. Zeno, on the other hand, has a wire overhead of 5 bytes.
5 from over 50.
5. And it can run in less than 200 bytes of memory.
That is a massive difference.
It's orders of magnitude. It means you can run Zeno on those tiny microcontrollers in the door handle or the tire pressure sensor. DDS is just too big for those. With Zeno, you can speak the same language from the tiniest sensor all the way to the central brain and even up to the cloud.
No more translation layers. It unifies the stack.
Exactly. And it solves the DDS discovery storm problem on Wi-Fi. It's also becoming the preferred middleware for robotics and ROS2, the robot operating system.
And since autonomous cars are basically big robots.
That's the convergence. The convergence of ROS2 and Zeno is a major strategic trend for this 2024-2026 window. If I were an architect today, I'd be looking very, very hard at Zeno.
So if I summarize the nervous system recommendation, move to Ethernet with TSN for the plumbing, and seriously evaluate Zeno for the application layer.
That is the architect's recommendation, yes.
All right, we built the body, we've wired the nervous system. Now let's look at the brain itself. Section 3. The hybrid brain, operating systems, and mixed criticality. And that word hybrid is key. We used to think we'd have one OS to rule them all.
Right, one giant Windows or Linux for the entire car, but we realized that's impossible because of mixed criticality.
Which is the hardest problem in safety engineering.
It really is. It's the challenge of running a safety critical system, like your brakes, which are ASIL-D, on the same chip as your infotainment app, which is QM.
Let's define those acronyms. Not everyone lives in the world of ISO 26262.
Sure. ASIL-D stands for Automotive Safety Integrity Level D. It's the highest level of risk management. It means if this system fails, the probability of fatal injury is high. Brakes, steering, airbags, and QM. QM is quality managed. That basically means try not to crash, but if you do, it's just annoying, not deadly. Your music player, the ambient lighting, Angry Birds.
So the problem is, on a centralized chip, these two live next door to each other. You cannot let the crashing music player take down the braking system.
Never. If your map app freezes, the airbag must still deploy. That's why we use hypervisors. Technologies from QNX or Green Hills, they create virtual walls inside the chip. We call it freedom from interference.
But within those walls, we're seeing a 3-layer OS strategy emerge. So let's unpack that. Layer 1, the experience layer.
This is almost exclusively becoming Android Automotive OS, or AAOS. This is for the UX, the apps, the ecosystem. You can't build a better app store than Google. You just can't.
But automotive engineers traditionally hate Android.
They do, because it changes every year. A car lasts 15 years, and Android developers know nothing about car physics.
So how do you bridge that gap? How do you let an Android dev open the sunroof without compromising safety?
The report highlights a tool from Electrobit called EB Corbos Link. It's brilliant. It's a translator. It lets an Android developer write code that interacts with vehicle signals, like get battery status, without ever needing to know about the complex AutoSAR stack underneath.
It decouples the fun development from the safety development.
Perfectly. Which brings us to layer 2, the safety compute layer.
This is where the heavy lifting happens. Sensor fusion, path planning.
The decision-making of the car. And the strategic shift here is massive. The move to secure Linux.
Now, secure Linux sounds like an oxymoron to some traditional auto engineers. Linux is open source. It's the Wild West. How do you make it safe enough for SLB-ADD?
That's the challenge Electrobit is solving with EB Corvus Linux for safety applications. It's based on Ubuntu, so you get that massive ecosystem of tools, but it's hardened. They use tools like ELOS for event management and Crinit for state management.
Simplify that for us. What do ELOS and Crinit actually do?
Okay, so Crinit is a specialized init system. It creates a very strict boot process. It ensures only trusted processes start and in the exact right order, no rogue processes. ELOS then manages the communication between those processes, so if one crashes, it doesn't corrupt the others. It's a safety net around the Linux kernel.
And the reason for moving to Linux in the first place is the maintenance, right?
100%. If you build your own proprietary OS, you own the maintenance for 15 years. Every security patch, every bug fix, it's incredibly expensive. If you use Linux, the global community maintains the kernel. You just have to harden it. It's the only way to survive that 15-year life cycle.
And finally, layer 3, the lean edge. We're not running Android on a Windows switch.
No, that would be incredibly wasteful. For the edge windows, seats, lights, we're seeing a lean strategy. The solution highlighted is EB Triso's AutoCore Lite.
What makes it light?
It strips away the heavy runtime environment of standard AutoSAR. It uses optimized CAPIs. It's designed to run on tiny, low-cost microcontrollers like Cortex M0 Plus chips with less than 512 kilobytes of flash.
The penny pinching layer.
And you have to pinch pennies there. If you save $2 on every door controller and you make 5 million cars, that's $10 million straight to the bottom line. The strategy is don't put a heavy OS where you don't need it.
So, the summary of the brain. Android for the screens, secure Linux for the thinking, and lean AutoCore for the hands and feet.
That is the winning architecture for 2026.
Okay, we have the design, but now comes the hardest part, actually building it. This brings us to Section 4, the industrialized software factory, DevOps and virtualization. This is where the decoupling paradox gets solved.
It has to be solved here. The mantra in the industry right now is shift left or die.
Shift left. It's corporate speak, but what does it actually mean in practice?
It refers to the timeline. Time moves left to right. Shift left means doing things earlier. Traditionally, software validation happened on the right after the hardware was built. You got the prototype, put the software on it, and drove it around.
And if you found a bug then?
It was too late. Fixing a bug at that stage costs 100 times more than fixing it during design. So you must move validation to the left before the hardware even exists.
Because if you wait for the B sample, the physical prototype, to start testing your software, you're already 2 years behind schedule.
You will miss your SOP date. Guaranteed. The solution is virtual engineering. But we're not just talking about generic simulation.
Right. There's a specific concept here that blew my mind, bit parity.
Yes. This is absolutely crucial. In the past, simulation was often a video game version of the car. It behaved like the car, but the code wasn't the same. Bit parity means the binary code, the actual ones and zeros running on your AWS server, is identical to the code that will run on the chip in the car.
How is that even possible? A server uses an Intel chip. The car uses a specialized NXP chip. They speak different languages.
It's possible through deep collaboration. The report cites NXP CoreRide working with Synopsys VDK, their virtualizer development kit. They have created virtual versions of the S32Z and S32E chips that run in the cloud. They emulate the exact instruction set, the registers, everything.
So I can compile my braking software, deploy it to a virtual chip in the cloud, and know for a fact it will run exactly the same way on the physical car.
Correct. And you can debug it there, too. There's a collaboration between Lauterbach, the gold standard for hardware debugging, and NXP called Debug as a Service.
Debug as a service. I love that.
Imagine you're a developer in Bangalore. The physical prototype board is in a lab in Detroit. In the old days, you'd have to fly there. Or call a guy in Detroit and ask him to go hook up a probe.
A process that takes days.
Now, with these hardware farms, you open your browser, you connect to a rack of chips or a purely virtual chip, and you get your trace data, your step-by-step debugging right there. No hardware on your desk required.
That is a complete game changer for speed.
It removes the hardware bottleneck entirely. You can hire 500 software engineers, and they can all start coding and testing on day one, even if the chip hasn't been manufactured yet.
And this extends to calibration, too. The Horibamira Mobius case study in the report is fascinating.
Oh, Mobius is incredible. This is about vehicle dynamics. Calibrating an EV powertrain usually takes months of driving around test tracks. Engineers just driving in circles, tweaking the torque map.
Trying to find that perfect balance of fun versus efficiency.
Right. It takes forever. Mobius uses AI to condense that. They take, say, 10 hours of real-world driving data and use AI to condense it into a 2-hour high-intensity virtual cycle that covers all the same edge cases.
So you test faster.
Much faster. They cite a 70% reduction in physical testing time. But more importantly, the AI found optimization patterns that humans missed. They achieved a plus 19% energy efficiency gain just through this AI-driven calibration.
19%. That's free range. That's range you got just by writing better software.
Exactly. And they even include subjective tuning. They put a human in a simulator loop to feel the calibration before the car is built. So you know if the acceleration feels sporty or sluggish without ever building a prototype. You tune the soul of the car in the cloud.
This is that industrialization we talked about, moving from craftsmanship to factory production of software.
It is. And if you aren't doing this, if you don't have bit parity and AI calibration, you simply cannot compete with the speed of the Chinese OEMs or Tesla.
Speaking of competition, let's move to Section 5, Regional Analysis and Market Maturity. We have a framework here from Here Technologies and Omdia, the 4 phases of SDV maturity.
It's a good yardstick to measure where companies actually are versus where their marketing says they are.
Phase 1 is connected, basic OTA updates. Most cars are here. Phase 2 is augmented, customizable features. Phase 3 is adaptive, which they say is the turning point for ROI.
That's where the car learns, adapts, you can subscribe to major new functions.
And Phase 4 is agentic, AI-driven, predictive.
The reality check is that most of the legacy industry is currently stuck in the mud between Phase 1 and Phase 2. They're connected, but they aren't truly adaptive because their underlying architecture just isn't ready.
Okay, let's look at the regions. China.
The report calls them the aggressor, and for good reason. They are operating on 18-month development cycles.
18 months. A traditional Western car is 4 to 5 years.
They're moving 3 times faster. Their willingness to adopt these Phase 3 ecosystems now is high. Companies like BYD and NIO are vertically integrated. They make the battery, the chip, the software.
They don't have to negotiate with 20 different suppliers.
Right, and they treat the phone and the car as one device. That mobile plus car fusion is seamless. They're skipping the awkward teenage phase of SDV and going straight to adulthood.
Okay. North America.
The compute heavyweights. This is Tesla, but also the tech giants influencing the OEMs. The focus here is on high compute power, like that NVIDIA Thor chip and total cloud dominance. They're betting that whoever owns the biggest brain and the best cloud pipeline wins.
And Europe.
The safety guardians. Europe is struggling. They have massive organizational inertia. Conway's Law is hitting them hard.
Conway's Law.
The idea that your product's architecture will mirror the communication structure of your organization. European OEMs have these 50-year-old silos for body, chassis, powertrain. These silos don't want to talk to each other, so the car's architecture ends up fragmented.
But their strength is in standards.
Yes. They are defining ISO 26262, the new cybersecurity regulations. They're building open source alliances like Eclipse SDV to try and pool resources.
So Europe is trying to standardize its way to survival, while China sprints and America computes.
That's a very fair summary.
All right, we've covered the report. We've seen the architecture, the nervous system, the brain, the factory, and the global battlefield. Now, consultant, it's time for the verdict. What are our strategic recommendations?
If I'm advising an OEM CTO today, based on these sources, there are 4 non-negotiable action items.
Action item 1.
Buy platforms. Don't build plumbing. Stop trying to build your own OS from scratch. It is a trap. Use pre-integrated stacks like NXP CoreRide, use Vector's base layer, use EB Corbos. Focus 100% of your internal resources on the app layer. Nobody buys a car because of its bootloader.
Action item 2.
Refactor your middleware. If you're designing a zonal architecture for 2026, you must seriously evaluate Zeno or DDS. Relying on SOMI IP is going to choke your data flow. You need that 5x overhead efficiency to scale.
Action item 3.
The hybrid factory. If you are not debugging the cloud with bit parity, you are already dead. You have to enable your developers to work remotely, instantly, and on virtual hardware that matches the car. If you're still waiting for physical boards to show up, you are too slow.
And the final one, action item 4.
Organizational change. This is the hardest one. You have to break Conway's Law. You cannot build a centralized software architecture with a decentralized, siloed organization. You have to move from component teams, team chassis, team body, to feature teams, team automatic parking, team smart entry. Your organization must mirror the architecture.
Powerful stuff. The goal is no longer just to build a car.
No. The goal is to build a platform that survives for 15 years. The hardware is just the vessel. The value and the survival of the company depends on the platform's ability to evolve over time.
The winners will be those who can finally decouple their software speed from their hardware constraints.
That's the whole game.
Well, that concludes our deep dive into the 2024-2026 Global SDV Strategy Report. It's daunting, but the path is clear. The technology exists. The challenge now is execution.
The tools are there. The roadmap is there. Now it's just about doing the work.
As the report says, let's get back to the lab. The code won't write itself. Thanks for listening to the deep dive. We'll see you next time.